Morning, students. Today we will discuss the first session in the VLSI subject, that is the basics of VLSI. In that, we will begin with the basics of digital system design. And coming to that, here we see the semiconductor family and its evolution diagram. So here, if we observe the basics of the basic component like diodes and transistors, usually the semiconductor material from which we use like p-type and n-type, from that we have the diodes and the transistor design, and from that the diode and transistor logic, this is DTL logic. And by using the transistors we have two different type of transistors. They are BJT and FET. That is nothing but bipolar junction transistor, which is a current control device, and FET is nothing but a voltage control device. And if we observe first one, the diode transistor logic DTL here, both diode and the transistors are the key elements to implement the digital logic function. And if we use the transistors as the key components, they we have, if we using the BJT logic family, we have three different type of logic families. They are TTL, RTL and ECL. TTL is nothing but transistor logic, so which is operating as a switch to perform the logic operations, and RTL is nothing but resistor transistor logic, and ECL. ECL is nothing but emitter coupled logic, which is a high speed IC bipolar transistor family. So from that we are going to design the logic gates, and from that we are going to design the ICs, which we are going to combine millions or billions of transistors on a single chip. And if we use the FET as a basic component, then here here we have two different type of FETs. They are JFET and MOSFET. If we see the abbreviations, they are junction field effect transistor and metal oxide semiconductor field effect transistor. We all know that usually the JFET, it will only operates in the depletion mode, and MOSFET, it operates both in depletion and enhancement mode. Usually the JFET is used for low noise applications and MOSFET is used for high noise applications. So overall we'll be using the MOSFET and for the design of ICs. Here if we observe in the MOSFET also, we'll be having the different types. They are, first one is N-channel MOSFET, and another one is P-channel MOSFET, and the third one is CMOS. CMOS is nothing but complementary metal oxide semiconductor. Here we are using both NMOS and PMOS for the design, and we'll see them in the next sessions deeply. And after that, with the help of those transistors, we are going to design the logic gates, and from that we are going to design a complex IC designs, and those ICs, based upon the number of components which we are placing them in a single chip, they are divided it into different categories like different levels of integration. That is nothing but, if we use a small number of transistors like hundreds of transistors in a single chip, then it is called as small scale integration. Like that, if we use some more number of transistors like thousands of transistors, like we can say that it is a medium scale integration. And if we use more than 10,000 transistors, if we place in a single chip, then we call as a large scale integration. And after that, if we're using more than millions of transistors in a single chip, then we can call it as a very large scale integration. And like that, it is a endless journey. So now if we see the process of designing a digital logic system, mainly the they are depending upon the density, functionality, and the features. If we observe, these three are very important for the evolution of a IC. So first of all, what is meant by density? It is that the number of components like transistors or gates that are integrated on a single chip, and then the functionality. With higher density, the ICs can perform more complex functions on a single chip. So, the functionality increases as multiple components are integrated. Usually, if we observe, earlier ICs only perform the logic operations, but now modern ICs can run um, with full processors, memory modules, and advanced communication systems on one chip. And there are different features that is nothing but the capabilities and performance improvements of ICs. We all know the features of the IC is depending upon the speed, power efficiency, and the area. Actually, we all want an IC to be working at some faster or with some faster operations and with low energy consumption and also with the smaller size. So these features has to consider when we are designing some system. And moving to the general design flow initially, so process of designing a digital logic system with minimizing the cost and the logic levels and propagation delay and with the help of optimizing the performance. Further, the first step to design is a design specification. The specification is nothing but what we require, the system requirements. We need to know about the system requirements or this functionality, what we have to define for the system. We need to specify those things first. And after that, the truth table. The truth table is nothing but the logic relationship between the input and output, which is derived for logic equations, which is helpful for designing. And after that, we are going to reduce the logic equation with the help of Boolean algebra or with the help of a K-map to minimize the number of terms and logic gates required for the design. And after that, we are going to minimization of logic and multi-level optimization. That is nothing but optimizing the design by balancing both the cost and the performance. Here cost is nothing but we are going to reduce the number of gates, and performance is we are going to reduce the propagation delay. And after that, we are going to see the we are going to examine the available inventory. So like existing hardware like logic gates like IC74007432, they are reviewed to determine which can be efficiently utilized. Like that, this is the initial design flow. Coming to that, when we are going to implement a combinational logic function with the help of these steps, with the help of these design flow, how we are going to implement. Sorry. If we see first initial, we all know that the design specifications, we need to specify which input has to taken and which output has to be taken, how many inputs have to take for input and how many outputs have to consider for the design, and the truth table for the input and for the output. We have to draw the truth table, and after that we are going to reduce the equations by using the K-map or Boolean algebra, and after that we are going to minimize the gates, and we are going to reduce the propagation delay, and we are going to examine the available inventory previously I have said, and after that we are going to implement it in the NAND implementation. Now, what is the advantage of using the NAND implementation is nothing but the NAND is a universal gate, means any logic we can be implemented with the help of this NAND gate, and these are cost effective and they can reduce the complexity in the design. So we prefer to design it in the NAND implementation. Now here if we see here, there are two examples if we consider here. For first example, that is x is equal to AB whole bar into CD whole bar into BD whole bar, like that. In this example, if we implement all these steps, we are implementing this with final design will consisting of 27400 ICs, 17430 and 2 level of logic. First logic synchronization, sorry, and 7474 for logic synchronization. And if we implement this second Boolean equation, then it requires 27408 gates, 37432 gates, 3 level of logic, and 17474 for synchronization. So if we observe here, in the first example, we'll be getting the propagation delays, fast propagation delays. But for the second example, it leads to some propagation delay higher compared to that of the first design. So by optimizing the Boolean equation and choosing the correct ICs, the design can achieve the balance of speed and cost. So students, just try considering this example and implement this all the design steps. See here, now we are going to design one digital system. The specifications of the design here are, if logic 2 or 2 greater than 2 input is 1, then only the output will be 1. So consider this logic, means if two inputs or more than two inputs of input is 1 only, then only the output will be 1. And for remaining the conditions, the output will be 0. So take that logic and draw a truth table for here. If we consider in this example, we have 4 inputs A, B, C, D. Right. So if we consider two inputs, like if we consider how many 4 inputs means we have 16 combinations. In that 16 combinations, if we have two inputs or more than two inputs is 1, then the output is 1. And for all the remaining conditions, the output will be 0. So like that, draw the truth table for this. And from that, you have to reduce the equations by using K-map and take the Boolean equation and rewrite with the help of an AND implementation, and you can derive the final steps. Thank you students, and in the next session we'll be discussing the basics of VLSI.